Welcome to this video where we explore LeetCode problem number 782, transform to chessboard. In this challenge, we'll dive into binary matrices and figure out how to determine if they can be rearranged into valid chessboards. Stick around as we break this problem down step by step. In this problem, we are given an nxn binary matrix called board, and the goal is to transform it into a valid chessboard. A chessboard is a specific pattern where no two adjacent cells are the same, and the rows and columns alternate in a defined pattern. For instance, each row and column must follow an alternating sequence of zeros and ones, such as 0, 1, 0, 1, or 1, 0, 1, 0. Additionally, no two rows or columns can be identical, nor can they be exact inverses of each other. To achieve this transformation, we are allowed to make moves, where each move consists of swapping two rows or two columns. The task is to calculate the minimum number of these moves required to create a valid chessboard, or determine if it's impossible to do so. If it's impossible, we return -1. The input is a binary matrix, and our output is either the minimum number of moves or -1 if the transformation cannot be done. To better understand the problem, let's consider some examples. In the first example, we are given a 4x4 board as input. The matrix is shown here, and the output for this board is 2. This means that we can transform the given board into a valid chessboard with just 2 swaps. Now, we'll delve into the explanation of how these swaps achieve the desired result. For the first example, the explanation shows the steps required to transform the board. The initial board is already close to a valid chessboard, but some adjustments are needed. First, we swap row 1 with row 3, which aligns all the rows in the correct alternating order. Next, we swap column 1 with column 3, ensuring that all the columns also follow the alternating pattern. After these 2 swaps, the board becomes a valid chessboard, with rows and columns both alternating perfectly as required. This demonstrates how the minimum number of swaps, 2 in this case, can achieve the transformation. Now let's move to another example where no swaps are needed. In the second example, the input is a 2x2 board. The output here is 0, indicating that no moves are required. This is because the given board is already a valid chessboard. The rows and columns alternate perfectly, and no adjustments are necessary. This serves as a simple case where the board meets the chessboard criteria from the start. However, not all boards can be transformed into a valid chessboard, as we will see in the next example. In the third example, the input is another 2x2 board, but this time the rows are identical. The output is -1 because it is impossible to transform this board into a valid chessboard. The reason is that the rows are the same, which violates the chessboard property that no two rows or columns can be identical. This example highlights the importance of the structural constraints in determining whether the transformation is feasible. Let's now review the broader constraints and key points for solving the problem. The constraints for this problem specify that the board will always be an nxn matrix, with n ranging from 2 to 30. Each cell in the board contains either a 0 or a 1. These constraints ensure that brute force approaches, which might involve testing all possible swaps, are computationally infeasible. Instead, efficient algorithms are required to determine the minimum number of swaps or to decide if a transformation is impossible. Key points to remember include the alternating pattern requirement for valid chessboards, the prohibition on identical or inverse rows and columns, and the need to calculate swaps efficiently. Together, these insights will guide us in solving the problem effectively. To tackle the problem of transforming a binary matrix into a valid chessboard, we need to understand the problem's constraints and challenges. A chessboard alternates between zeros and ones in both rows and columns, ensuring no two adjacent cells share the same value. One approach we might first consider is brute force. The intuition here is to generate all possible valid chessboards of size nxn and then check if the given board can be transformed into one of these valid configurations. For each transformation, we would calculate the number of swaps required. However, this method faces significant challenges. Generating all possible chessboards becomes computationally expensive very quickly, as the number of permutations grows exponentially with the input size. This makes the brute force approach infeasible, especially for larger boards, as its time complexity is exponential. While it helps to understand the problem, we need a more practical solution for real-world scenarios. A more efficient method is the optimized approach. This builds on key observations about the structure of a chessboard. First, for a board to be transformable, the rows and columns must either be identical or complements of each other. Additionally, the number of ones in every row and column must be equal or differ by at most one. Another critical property of a valid chessboard is that it alternates between two patterns, one starting with 0 and the other starting with 1, such as 0101 and 1010. Using these insights, the optimized approach proceeds in 3 steps. First, we verify that the board satisfies these fundamental properties. Next, we count the number of swaps needed to rearrange rows and columns to match the alternating patterns. Finally, the minimum number of swaps required is returned. The efficiency of this method lies in its time complexity of n squared, which makes it scalable even for larger matrices. An alternative we might consider is a greedy approach, where we focus on transforming rows and columns independently to align with the desired pattern. However, this can fail when global constraints, such as interdependencies between rows and columns, are ignored. This highlights why the optimized approach is more robust. Among the various methods, the optimized approach stands out as the best choice due to its balance of correctness and efficiency. By leveraging the inherent properties of a chessboard, we can systematically determine whether the board is valid and calculate the minimum swaps required without unnecessary complexity. The key insight here is recognizing that rows and columns must follow strict alternation rules. This eliminates the need to generate all possible chessboards and reduces the problem to verifying patterns and counting mismatches. This realization acts as the aha moment for the problem, turning what initially seems complex into a straightforward counting exercise. Comparing this with other approaches, brute force is simply too slow for larger boards, while greedy methods, despite being faster, risk failing due to their inability to account for global constraints. The optimized approach avoids both pitfalls, making it the ideal solution for this problem. The optimized approach is not just effective but also computationally efficient. Its time complexity is n squared, as we verify the board and calculate swaps based on its rows and columns. The space complexity is 1, since we don't require any additional data structures beyond simple counters. This low overhead ensures that the solution scales well with input size. What makes this approach particularly suitable is its reliability in meeting the problem's constraints while minimizing computational effort. By focusing on verifying the alternating patterns and counting mismatches, we avoid the exhaustive exploration of brute force and the potential pitfalls of greedy methods. This combination of correctness, efficiency, and simplicity is why the optimized approach is the preferred strategy for solving the transform to chessboard problem. To begin, the problem asks us to determine if a given nxn binary matrix can be transformed into a valid chessboard. A chessboard alternates between zeros and ones in both rows and columns. If the transformation is possible, our task is to calculate the minimum number of row or column swaps required to achieve the desired pattern. The first step in solving this problem is to validate whether the input matrix can even resemble a chessboard. First, we check row and column uniformity. The initial row of the matrix defines the alternating pattern, so all other rows and columns must either match this pattern or be its binary complement. For example, if the first row is 0, 1, 0, 1, valid rows would include 0, 1, 0, 1, or 1, 0, 1, 0. Next, we ensure that the counts of rows and columns with these patterns differ by at most 1, which is necessary for alternating arrangements. Additionally, we account for edge cases like the size of the matrix. If n is odd, the counts may differ by 1, if n is even, the counts must be exactly equal. These validations establish whether a transformation is theoretically possible. Once we confirm that the matrix can be transformed into a chessboard, the next step is to calculate the minimum number of swaps required to achieve this. To do so, we divide the process into 2 parts, row swaps and column swaps. For rows, we determine how many of them deviate from the expected alternating pattern based on the first row. For example, if the first row is 0, 1, 0, 1, we calculate the number of rows that don't follow this pattern and adjust them using swaps. Similarly, for columns, we count how many deviate from the expected pattern and adjust them as needed. The total number of swaps is the sum of the row and column swaps. Importantly, no swaps are necessary for rows or columns that already follow the alternating pattern. This step ensures that we achieve a valid chessboard with the minimum possible transformations. Now, let's focus on some key insights that can help us understand the algorithm better. First, the core property of a chessboard is its alternating pattern of zeros and ones, ensuring no two adjacent cells in a row or column are the same. To validate this, the first row serves as our reference pattern, and all other rows and columns must either match it or be its binary complement. Another important insight is that row and column swaps can be handled independently, meaning we can focus on correcting one dimension at a time without affecting the other. This symmetry simplifies the process. Additionally, the algorithm is optimized to be efficient. Validating the matrix to check for chessboard properties has a time complexity of O(n) squared, while computing the swaps is linear, or O(n). This efficiency ensures the solution is scalable even for larger matrices. Finally, we rely on straightforward data structures like counters to track patterns and deviations. For those looking for further optimization, binary patterns can also be represented as integers for faster computation. The algorithm's complexity is straightforward and efficient. The time complexity is O(n) squared, stemming from the need to validate every cell of the matrix during the initial checks. Calculating the swaps is linear, or O(n), since it only involves comparing row and column patterns. Space complexity is O(1), because no additional data structures are needed, we work directly with the input matrix and a few counters. It's also crucial to address edge cases. For example, if rows or columns are non-alternating and do not match the reference or complement patterns, the transformation is impossible, and we return -1. We also handle matrices of both even and odd dimensions carefully, ensuring the counts align correctly for alternating patterns. If the matrix is already a valid chessboard, the result is simply zero swaps. Finally, we account for cases where the transformation is infeasible due to incorrect structure, allowing us to exit early and save computation. To solidify our understanding, let's look at a visual example. Consider the input board 0, 1, 0, 1, 0, 1, 0, 1, 0. First, we validate the matrix. The first row is 0, 1, 0, and the other rows either match this pattern or its complement, so the matrix satisfies the chessboard criteria. Since no rows or columns deviate from the alternating pattern, no swaps are needed, and the output is 0. Now, take another example, 1, 0, 1, 0, 1, 0, 1, 0, 1. The first row is 1, 0, 1, and although other rows match the pattern, swaps are required to align the rows and columns into a valid chessboard. After calculating the necessary adjustments, we determine the minimum number of swaps required to achieve the transformation. This step-by-step validation and adjustment process ensures that we handle all possible cases effectively. Here, we're implementing the function moves to chessboard within the solution class. The first step is to determine the size of the board, which we store in the variable n. Then, we check if the board's pattern is valid for transformation into a chessboard. This is achieved through a nested loop that iterates over every cell in the board. Using the XOR operation, we verify that the top left corner, the current row, and the current column align with the chessboard's alternating pattern. If at any point this condition is not satisfied, the function immediately returns -1, indicating that the transformation is not possible. Next, we calculate the imbalances in the rows and columns. First, we compute row_sum and col_sum, which count the number of ones in the first row and first column, respectively. These sums help us determine if the board has the correct number of ones and zeros for a valid transformation. We also calculate row_swap and col_swap, which measure how many rows and columns deviate from the desired alternating pattern. For rows, we check if the value in each row matches the parity of its index, and for columns, we do the same for each column index. Finally, we validate the row and column sums to ensure they fall within acceptable ranges, which are determined based on whether n is even or odd. If these conditions are not met, we return -1 to indicate the board cannot be transformed. If the board passes all the earlier checks, we need to determine the minimum number of swaps required to achieve the chessboard pattern. When n is odd, the parity of row_swap and col_swap must be adjusted to ensure they are valid. If either of these is odd, we subtract it from n to calculate the correct number of swaps. On the other hand, if n is even, we take the smaller value between row_swap and n row_swap, and similarly for call_swap. This ensures that we minimize the number of swaps needed. Finally, we compute the total swaps required by summing row_swap and call_swap, then dividing by 2. The division by 2 is important because each swap operation affects both rows and columns simultaneously. The function then returns this final value, which represents the least number of swaps necessary to transform the given board into a valid chessboard. Here, we start by defining the moves to chessboard method, which takes a 2D integer array board as input. The first step is to validate whether the given board pattern can be transformed into a chessboard. To do this, we use nested loops to iterate over all pairs of rows and columns. The condition board 0 0 board I 0 board 0 j board I j equals 0 checks if the XOR of the top left corner with other positions violates the alternating pattern required for a chessboard. If any position fails this check, we return -1, indicating the transformation is not possible. Next, we initialize variables to count the imbalances in rows and columns. Rowsum and callsum keep track of the total number of ones in the first row and first column, respectively. Meanwhile, rowswap and callswap count the positions in the first row and column that do not match the expected pattern of alternating zeros and ones. These counts will help us determine the minimum number of swaps needed later. Now, we validate the sums of the rows and columns. For a valid chessboard, the number of ones in the first row and column must lie within a specific range, determined by the board size n. If the rowsum or callsum is out of bounds, we return -1. Next, we handle the swaps. If n is odd, we can only use one of the two possible swap configurations, so we adjust rowswap and callswap to ensure they are even. For even-sized boards, we take the minimum of the current swap count and its complement, n rowswap or n callswap. Finally, we calculate the total number of swaps needed by summing rowswap and callswap, dividing by 2 to account for the fact that each swap fixes 2 positions. The result is returned, completing the transformation process. Here, we begin with a simple 2x2 board where the input is given as a matrix. The first step is to check if this board can be transformed into a valid chessboard. To do this, we calculate the size of the board, n, which is 2 in this case. Next, we ensure that the XOR condition is satisfied for all indices. This condition ensures that the board alternates between 0 and 1 in a chessboard-like pattern. For each combination of I and j, such as 0, 0, 0, 1, 1, 0, and 1, 1, the condition holds true, meaning this board is a valid candidate for transformation. Afterward, we calculate the sum of the first row and the sum of the first column. Both sums turn out to be 1 because there's exactly 1 1 in each row and each column in the given board. The next step is to count the number of row and column swaps needed to transform the board. For row swaps, we compare each element in the first column with its expected value based on the row index. The calculation reveals that both rows already align with the ideal chessboard pattern, so row_swap is 2. Similarly, for column swaps, we compare the elements of the first row with their expected values based on the column index. Again, both columns align perfectly, resulting in call_swap being 2. Since n is even, we adjust these counts by taking the minimum of the swaps and their complements. This adjustment gives us row_swap and call_swap as 0 each. Finally, the total number of swaps needed is calculated as the sum of row_swap and call_swap divided by 2, which results in 0. Thus, no swaps are needed to transform this board, and the output is 0. Now, we look at an example where the input board has an invalid pattern. For this 2x2 board, we again start by determining the size, n, which is 2. Next, we check the XOR condition to see if the board can be transformed into a chessboard. While iterating through the indices, we find that the condition fails for the combination I, j equals 0, 1. Specifically, the XOR of the elements at this index does not equal 0, indicating that the board does not have the alternating pattern required for a valid transformation. Since the board fails this critical check, we conclude that it cannot be transformed into a chessboard, and the output is -1. For a larger example, consider a 4x4 board. Here, the first step is to verify if it can be transformed into a chessboard. After calculating n is 4, we check the XOR condition across all indices, and it holds true for every combination of I and j. This confirms that the board has a valid alternating pattern. Next, we calculate the sums of the first row and the first column. Both of these sums equal 2, as there are 2 ones in the first row and 2 ones in the first column. We then count the imbalances by determining the number of elements in the first column and first row that align with their expected chessboard values. Both row_swap and col_swap are calculated as 4, indicating that each row and column requires adjustments. Since n is even, we adjust these counts by taking the minimum of the swaps and their complements. This adjustment results in both row_swap and col_swap being reduced to 0. Finally, with the adjusted swap counts, we calculate the total number of swaps needed to transform the board into a chessboard. The formula for total swaps is the sum of row_swap and col_swap divided by 2. Substituting the values, we get 0 plus 0 divided by 2, which equals 0. This means that the given 4x4 board is already in the correct configuration and no swaps are needed. Therefore, the output is 0. The time complexity of our solution is n squared, and this primarily comes from the validation process. First, we need to check if the given board can actually be transformed into a valid chessboard. This involves a nested loop that iterates over all the nxn cells of the board. For each cell, we perform an XOR operation combined with a condition to ensure the board adheres to the chessboard pattern. Since these operations are constant time, O(1), performing them for each of the n squared cells gives us a time complexity of n squared for this step. Next, we calculate row and column imbalances. Summing the first row or the first column individually takes n time for each, and both row and column swaps involve iterating through all rows and columns, respectively, which also costs n. Combining these smaller operations results in an additional n, but the dominant term is still n squared. To continue analyzing the time complexity, let's consider the validation of row and column sums. Checking the values of row_sum and col_sum involves simple conditional checks, each of which takes constant time, or O(1). Similarly, adjusting the swap counts in cases where n is odd involves basic arithmetic and conditional checks, which also run in O(1). Finally, the calculation of the total swaps, which is done by combining row_swap and col_swap, is another constant time operation, O(1). When we sum up all these steps, we see that none of them exceed the n squared from the validation step, making n squared the overall time complexity of the solution. Now, let's analyze the space complexity of the solution, which is O(1). First, the input board is an nxn matrix, but since this is part of the input itself, it doesn't count as additional space. The algorithm uses only a fixed number of auxiliary variables, such as row_sum, col_sum, row_swap, col_swap, and a few loop indices like I and j. These variables do not grow with the size of the input, meaning their space usage remains constant. Additionally, the algorithm does not rely on extra data structures like arrays, hash maps, or lists to store intermediate results. Because no extra memory is allocated that scales with the input size, the space complexity of the solution is O(1). When comparing this approach to a brute force method, the benefits of optimization become clear. A naive approach would involve generating all possible permutations of rows and columns to check for a valid chessboard configuration. Since there are n permutations for both rows and columns, this would result in a time complexity of n(2), which is infeasible for even moderately sized boards. Furthermore, brute force methods often require additional space to store intermediate boards or permutations, leading to higher space complexity. In contrast, the optimized approach takes advantage of the properties of a valid chessboard, using efficient XOR-based checks and eliminating the need for permutations. This enables it to run in n squared time and use only O(1) space, offering significant improvements in both time and space efficiency. Let's break the time complexity down further by considering the best, average, and worst-case scenarios. In the best case, the board is already a valid chessboard. Even then, the nested loop validation still needs to process all n squared cells, resulting in a time complexity of n squared. In the average case, the board is partially valid, requiring additional steps like calculating and performing swaps. Despite these extra operations, the validation step still dominates, keeping the time complexity at n squared. In the worst case, the board is completely invalid and fails the validation check. Here too, the nested loops for validation iterate over all n² cells, so the time complexity remains n². In all scenarios, the dominant factor is the validation step, which ensures consistent performance regardless of the board's initial state. Finally, let's confirm the overall time complexity using a mathematical proof. The nested loops for validation traverse every cell in the nxn board, making this step n². All other operations, such as summations, swap calculations, and adjustments, are either linear in n or constant. Since these terms are negligible compared to n², they do not affect the overall complexity. Therefore, the time complexity of the solution is n². On the space side, we've already established that the algorithm uses only a fixed number of auxiliary variables, with no additional data structures, resulting in a space complexity of 1. This concludes the analysis, confirming that the solution is both time and space efficient. When solving this problem, there are several common mistakes that can trip you up. First, misunderstanding the rules of a valid chessboard is a frequent issue. Remember, a proper chessboard alternates between zeros and ones in both rows and columns. It's not enough to check just one dimension, you need to verify that the row pattern matches the column pattern as well. Missing this step can lead to incorrect outputs. Next, edge cases are another major source of errors. For example, non-square matrices, matrices where the counts of zeros and ones are unequal, or even matrices that already meet the chessboard condition. All of these scenarios need to be explicitly accounted for in your solution to avoid runtime errors or wrong answers. Another pitfall is confusing row swaps with column swaps. These two operations are not interchangeable, and their calculations must be handled separately. Finally, an often overlooked detail is the calculation of minimum swaps. Since there are two possible starting patterns, either 0 first or 1 first, you need to evaluate both and choose the minimum swaps required. Neglecting this can result in a suboptimal solution. Now, let's address another critical aspect: validating whether the matrix can even be transformed into a chessboard before attempting any swaps. Skipping this feasibility check can waste computation and lead to unnecessary complexity. Always verify the matrix by checking both patterns and counts up front. From an interview perspective, this problem is designed to test both your logical reasoning and your implementation abilities. Interviewers are particularly interested in how well you break down the problem into two distinct tasks: first, validating the chessboard constraints, and second, efficiently calculating the minimum swaps. Demonstrating a clear understanding of this structure is key. Additionally, optimization is a big focus here. Make sure to explain how your solution achieves n superscript 2 time complexity, where n is the size of the matrix. Be ready to discuss the trade-offs between code readability and performance, as interviewers often value candidates who can balance these aspects effectively. Now let's explore related problems and alternative approaches. In terms of related challenges, LeetCode number 296, best meeting point, involves minimizing distances in a matrix, which shares a similar grid manipulation aspect. LeetCode number 473, matchsticks to square, focuses on creating valid patterns under constraints, while LeetCode number 489, robot room cleaner, emphasizes grid traversal and recognizing patterns. Even LeetCode number 1010, pairs of songs with total durations divisible by 60, highlights modular arithmetic and pattern matching, which can be conceptually linked. As for alternative approaches, brute force is one option, where you check all possible row and column combinations and calculate swaps. While this is simpler to implement, it's highly inefficient, with exponential time complexity, and only practical for very small matrices. The greedy approach, on the other hand, is the optimal solution. It involves validating the chessboard constraints and calculating swaps for both starting patterns 0 first and 1 first, achieving n superscript 2 complexity. For advanced candidates, there's also the possibility of using bit manipulation to speed up row and column checks. While this can improve performance, it adds significant complexity to the implementation and can be harder to debug. Each method has its trade-offs, so it's important to choose the approach that best balances efficiency and simplicity for the given context. Great job making it through. We reviewed the transform to chessboard problem, focusing on analyzing matrix patterns and applying swaps. Remember to practice similar problems to enhance your skills. Don't forget to like, subscribe, and stay tuned for more coding insights. Thanks for watching. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!